All right, good morning, everyone. So, okay, the plan is we're going to do a review and then after that, we have time to work on the assignments and we'll talk about each one of those, point out some things, et cetera, et cetera. So, great. A review. So, first thing we did was chapter 26. So, to remind you, we started off, I'm going to throw in a little bit extra, but we started off with the potential of a continuous object. Where we actually officially started, and we said that the potential at a point P from a continuous object is equal to K integral dq divided by R. We're going to dq with the 10 to the fourth, so this was that equal to lambda dl, eta dA, or then rho dV, depending on the different geometries that we have. So again, this is line symmetry, this was an area symmetry, and then this was volume. Good. So this is where we actually officially started. Now, again, this technically is the potential difference at a point P relative to where it's 0, which is spatial infinity. So the thing is that this is my object, this is my point P. So again, this guy is relative to where this guy is equal to 0 when R is equal to infinity. So that's that part. Something else I'm going to throw in here as well, just for funsies, is remember that the change of potential, so we use this actually for capacitance, change of potential is equal to negative the integral from A to B, the electric field dotted by the differential length. So this will be important for if you're trying to derive, for example, capacitance. So cool. So those are those things. And then from there, we moved on to, speaking of capacitance, moved on to capacitance. Let's talk about capacitance. So capacitor. Am I going back? Yeah. Cool. So capacitors, we said, are two conducting objects which are separated by some sort of distance d. So here's conductor number 1, conductor number 2, separated by a spatial distance of d. So this is my capacitor. And again, if we plot the charge versus the potential, we find in this case is there a linear relationship between the two, where that slope is equal to what we call the capacitance. So the charge then is equal to the capacitance of the capacitor times then the potential, which means that the capacitance is then the charge divided by the potential. So that's that part. From here, we looked at a couple different capacitances, but the one that we're going to write down and use the most is actually for parallel plates. So let's say we have a parallel plate capacitor. So here, the parallel plate capacitor we found was that C was equal then to epsilon naught times the area divided by the distance. So a good one to know. Good. So here we looked at then connecting these guys in parallel and series. So let's look at parallel and series.
Will that mean that we have a parallel plate capacitor on the test?
Interesting question. Ultimately, I'm going to say in some form or another, yes. So, for example, some of the group assignments that we looked at where you had plates and then you separated them, and then you're looking at the work and how much potential was between the plates and energy stores and things like that. So most of that was done from parallel plate capacitors. So say yes at some point. So parallel and series. So in this case, we saw that if I have these guys in parallel, again, what's the same in parallel is that potential is the same. And in this case, we find that the equivalent capacitance is simply equal to the sum over all the pre-existing capacitors. And then for series, where here we have that the current is the same, that's an I, so it actually fits in there. Good. So that's my current. So in this case, we found the equivalent capacitance was actually the inverse. So the sum over all the inverses of the capacitances. So this is my parallel and my series.
Same, the
I current, or actually technically charge. I'll do it that way. Charge. But current and charge are the same thing, so but we call it charge. So let's call it charge.
Would that mean B is parallel?
Yes, correct. So instead of potential here, I could write B. Good. Yes. Okay. So from here, we looked at the energy stored. So we said that the energy stored was equal to the work done by the battery, which was then equal to 1/2 of many different things. So I can either have the charge squared divided by the capacitance, or the capacitance times the potential squared, or the charge times the potential. Where again, this one says that it's stored within the charge. It says it's stored within inside of the potential. And this one says it's stored within both. Or we can define our energy density, so little u, which is equal to capital U divided by the volume, which then works out to be 1/2 epsilon naught times the electric field squared, or this one says it's stored inside of the electric field.
Wait, what's little u?
Little u is called the energy density.
Okay. But that's not like J, right?
No, that's a current density. Yeah, so that's the next chapter. So this is energy density.
Is that Q on the top, the Q squared?
It's Q squared. Yeah. You can see my little square on there.
Just double check.
My little baby square. My daughter would say, oh, it's so cute.
Is that an E?
Which one?
The right one, E?
That's an electric field, magnitude of electric field square. Yes. Yeah, so this is little u is equal to capital U, which is this energy, which is the energy stored per unit volume. So this is technically energy stored.
And volume.
Volume, yeah, continuous bar is always volume.
What is the with line on top?
B with continuous line is volume, B with no line is velocity, and B with 2 bars, like that one over there, is potential. Okay. Finally, we looked at dielectrics. So we said the dielectric has a dielectric strength of what we call kappa, and what this does then is when I insert it inside of a capacitor, so that this is my dielectric with my dielectric strength kappa, then this thing increases the overall capacitance and it increases by an amount of the dielectric constant. So this is the effect that this guy has. Now again, the overall effect that this thing has depends on how I insert the dielectric, whether it's being connected to a battery or disconnected from a battery, so let's read through those things as well. So if it's connected to a battery, what happens in this case then is what? The potential stays the same. It doesn't actually change, so that's equal to the initial potential. Again, the capacitance changes, that simply increases by an amount of the dielectric constant. The electric field then also stays the same because I didn't do anything to that, so that stays the same. The charge then is going to increase by an amount of the dielectric constant, and the energy which is stored is then also going to increase by a factor of the dielectric constant. So this is the overall effect of adding a capacitor when it is being connected to the battery. If it is disconnected, in this case, what stays the same is the charge stays the same. The potential ends up decreasing by an amount of the dielectric constant, which means that the electric field also decreases by an amount of the dielectric constant, which means the energy also decreases by an amount of the dielectric constant. This is then the overall effect onto the circuits, or at least that's a capacitor anyways, when I connect the dielectric while it is fully charged, but it's disconnected from the battery. Okay. And one other thing I'm going to throw in here is that remember work is equal to negative the change in potential energy. So this is the work done by the electric field. This is going to be negative of the change in potential energy from the electric potential energy. So the electrostatic potential.
For disconnected.
I'm sorry?
What happens to the capacitance for the disconnected?
Oh, it stays the same. So same thing as before. Sorry. So capacitance is then just kappa times the original capacitance. Yeah. So the capacitance changes no matter what, exactly the same way. So putting in a dielectric just simply causes it to increase. And that was all chapter 26. So mostly just capacitor. Was okay? Not too bad. So let's talk about chapter 27. So chapter 27, we started looking in electrodynamics. So things are now actually moving and changing. So from here, we defined current was equal to the rate of change of charge. So this is current. And then we found if we put this into a circuit and we plotted then the potential versus the current, again, we get a straight line where the slope of the straight line is what we call the resistance. So Ohm's law then says that the potential is equal to the current times the resistance. Okay, this is technically only true in conductors, so metals, but okay, we didn't talk about any other case, so that's what you get. Resistance, we then said that resistance is two things. This is then equal to the potential divided by the current, but this is also equal to the resistivity times the length divided by the cross-sectional area. So this is then resistance. While resistivity is in general temperature dependent, so resistivity at a temperature T is then equal to the resistivity at a reference temperature, call it T0, times 1 plus alpha times the change in temperature. So alpha here is then just equal to the coefficient of thermal resistivity, I believe is what it's called.
So this row is material property.
This row is what?
Is this row a material property?
Yes, this is material dependent.
What's the alpha?
So the alpha is the coefficient of thermal resistivity. So this is also material dependent. And it exists within a certain range of temperatures, but again, this is just constant. So this is just something you would look up or I'd have to give it to you. Okay. So that's that guy. So what else we talk about? We talk about the current density. So the current density, at least the magnitude of the current density, is equal to the current divided by the area, which means that the current is related to the current density by the integral of the current density integrated over the area. So this is then just a weighted average of the currents over this. And for our cases, what we said is that this is going to be equal to 2 pi integral J as a function of R times R dr. So this is what this guy is going to equal to. So this is our current in terms of him. Now, going further with this, it turns out then that what if the current density is constant everywhere over the cross-sectional area, then we can rewrite this then in terms of what's called the drift velocity. So in this case, we find that the current then is equal to the charge times the number density times the area times the drift velocity. So this is if J is equal to a constant. And then from here, using our previous definition, this then tells me that J is going to be equal to Q times N times the drift velocity. So this is the relationship between the current density and the drift velocity and the currents and the drift velocity. So again, current is technically then just the average velocity at which these guys are moving. Now remember here, Q is the charge of the charge carrier, which if I'm talking about electrical circuit is going to be an electron. We call it a proton, but it's technically an electron. So in that case, this is then just going to be equal to E, and our fundamental charge. N is the number density. That's how many charge carriers I have per unit volume, which are allowed to move. So this is going to be your free electrons, which are inside of your conductor. And again, drift velocity is just the average speed at which it moves, even though it's trying to accelerate the entire time. Okay? What's up there, J? Constant. So these are only true when J is equal to a constant. Not necessarily. So if J is not equal to a constant, then you have to use this definition of the current, but then you can't directly relate this to the direct velocity. So that's about as far as you can go. Okay. What's up, Bing?
Can I see that last slide?
Sure. And then after this, we looked at what the microscopic version of Ohm's law.
So J is a function of R?
Correct.
Okay.
Yeah, so if J was a constant, this guy would simply come outside of the integral, and then you'd have the integral of R dr, which is just pi r squared, basically. So, okay. So we found the microscopic version of Ohm's law. So the microscopic version of Ohm's law says that the electric field is equal to the current density divided by the conductivity, which is the same thing as the resistivity times the current density, where the resistivity is inversely related to the conductivity. So again, all this thing says then is that what resistivity is a measure of how good of a resistor it is. Conductivity is a measure of how good of a conductor it is. So I can't have a good resistor and conductor simultaneously. It's one or the other. So it's either a good resistor or it's a good conductor. That's pretty much about it. Okay. So the last thing we then looked at was about power. So we said that the power loss was equal to the power delivered, which was then equal to one of three things: either the current times the potential, the current squared times the resistance, or the potential squared divided by the resistance, where the second two are good only for resistors. And then the first one is good for anything. Doesn't matter what it is. So whether it's battery or a capacitor or a resistor or whatever, doesn't matter. That works the same for anything. But yeah, these two, since they specifically talk about the resistance, that means they're only good for resistors. And that's it. That's all chapter 27. Finally, chapter 28.
Can you go back for a second?
No. Yes. Need to learn how to write that. What's up, Omar?
How do you feel about like equation or like the dielectric constant related to permittivity of free space?
For us, no, that won't be relevant. That won't be relevant. I mean, you could if you want to, but I gotta work. Wait, okay? Everyone's involved. Great. So chapter 28. So chapter 28, we started off by looking at this time resistors in parallel and series. So in this case, we said again, if we have parallel, again, what has to be true is that the potential is the same. And in this case, we inversely add all of our resistors together. So this is the opposite of that of conductors. But in series, which now the charge rate of change is the same, which means the current is the same. In this case, we add them all together, which again is the opposite of what we had for capacitors. So for capacitors, we added them inversely for series and added them directly in parallel. For resistors, it's just the opposite. Now, one thing we mentioned here is that, again, this only works for a single battery. So any single element or any circuit I have which has one single battery or one single EMF in it, then I can use this stuff. If that is not true, then in that case we have to use Kirchhoff's loop. So let's talk about the loop rule. So Kirchhoff's loop rule. So Kirchhoff's rules, number one is just conservation of energy, which says for a closed loop, the change of potential must be equal to 0 when I go from point A back to point A. So in this case, if I go from A back to A, through that closed loop has to be equal to 0. What's up?
Does the loop rule apply to every like situation? Like I know we didn't really use
Well, even those circuits we saw where we use parallel and series, you can absolutely do those using loop rules.
so you could still like do the system to
Yeah. Exactly. Yeah, so for example, the labs that we did this week, where you had the 3 different, or the 2 different setups there, even though we encourage you to use parallel and series to be able to analyze those, but you could absolutely use Kirchhoff's rules. It is general, it works in every scenario. So you don't need more than one battery to work with one battery. A good example of that would be the extra credit that I posted yesterday. So that one you actually have to use Kirchhoff's rules as well because of the placement of the battery. So what happens in that case is, since I got stuff over here, the battery's in the middle, then I have to actually use Kirchhoff's rules at some point because the placement of the battery is in between all that stuff. So I can't simply combine this side with this side because that means I'd have to move things over and change the geometry, but I can't change the geometry. So that's number one. Number 2 is conservation of charge, which says that at any junction, then the rate at which that charge is going through must be constant, which basically means that the sum of the currents going into the junction must be equal to the sum of the currents going out of the junction. Along with these were some sign conventions. So let's talk about our sign conventions. Let's talk about batteries first, or EMFs. So in this case, this is my point A, here is my EMF, so negative, positive, or B, and I go across it in this direction. So my potential at B minus potential at A is then equal to positive EMF. But if I go in the opposite direction, this direction from the positive terminal to the negative terminal, then my potential at A minus my potential at B is then a potential drop. For resistors, resistors are slightly more complicated because now I have to look at 2 things. Not only how am I going across it, but how the current is going across it as well. That's my resistor. And let's say my current is going this way across my resistor. So if I go in the same direction as, actually, taller. If I go in the same direction as the current, in this case, my potential at B minus my potential at A is then equal to negative I times R. So in this case, I get a potential drop. So if this is my point A, this is my point B. But again, if I go in the opposite direction as that of the current, I simply get a positive increase in potential. So in this case, my potential at A minus my potential at B is then a plus I times R. Finally, for capacitors, our last one says that if here are my capacitor plates, let's say this is my positive side, this then is my negative side, this is my point A, and this is my point B. So again, in the first case, I'm going to go across the capacitor from the positive plate to the negative plate. That then is a potential drop, dropped by negative Q over C. But if I go in the opposite direction, if I go from the negative plate to the positive plate, that is then a potential increase. So my potential at A minus my potential at B would then be plus over C. What's up?
So it's not dependent on like the.
It's not dependent on the direction of the currents.
Okay.
But in a way it is, because how this one is positively charged here and this one is negatively charged here means the current actually is going in this direction.
Oh, okay.
So you can think about it also again as if I'm going in the direction of the current, it's a drop. If I'm going opposite of the direction of the current, then it's an increase. But yeah, so So we don't mention it directly that it depends on the current, but the way that the plates are charged does depend on the direction of the current. So. Good. So that was all Kirchhoff's loop rules, and then after that we did what? RC circuits, right? So finally we have RC. So for RC we had for charging. We found was that the charge on the capacitor as a function of time is equal to the capacitance times the EMF times 1 minus e to the negative t divided by tau. And then that the current on the resistor as a function of time is then equal to the EMF divided by the resistance by Ohm's law, e to the negative t divided by tau, where tau is equal to R times C. Now again, this is technically only true if these guys are in series with each other. So make a little note of that. So here, everything has to be in series. So E, R, and C must all be in series. And then we also looked at discharging. Even though we didn't actually derive anything, we just kind of wrote it down based off of our knowledge. We said the charge on the capacitor as a function of time then is equal to whatever the initial charge was, e to the negative t divided by tau. And then the current on the resistor as a function of time then is equal to whatever the initial current was, e to the minus t divided by tau, where again, tau is simply the same thing. So R times C. And that's it. So good. So let's talk about what we're gonna see. So one thing we're definitely gonna see, definitely is Kirchhoff's loop rules. This would be long problem number 1. Now, I think I mentioned this in class yesterday, but basically this would be like a 3-loop circuit where again, only 2 of them are independent. The last one is independent, which means you have 3 currents and then you're only solving a system of 3 equations. So we're not gonna make it any bigger. We could, but for just to get the point across, that's about the simplest thing that we can actually do. So it'll definitely be one like that. Now, one thing I will say is that one will not involve capacitors. So it's only going to be this stuff that's here, which is batteries and resistors, which is what we focused on the most. So not RC circuits, but just regular resistive circuits. So definitely something like that. Another one problem will be, so let's go here. So basically kind of involving almost everything from chapter 27. So basically, you'll be given kind of like a simple circuit, so just a potential applied across the resistor, and then you'll have to find different things about it. So for example, what's the resistance, given that you know what the resistivity is, what's the current based off of like Ohm's law, because you have a potential on there, what's the current density, what's the drift velocity, basically things like that. So all little parts that all have to do with pretty much everything from chapter 27. There'll be some time dependence, or not some time dependence, but some temperature dependence in there too. So basically recalculate things you just did if the temperature increases from 20 degrees to like 100 degrees, something like that. What's up there?
So that rho at the rho L over A.
Yep.
Is that the rho of T at the top? Or is that
Well, that's just whatever. So this is rho. So this would be whatever rho it is I'm looking at. So if it was the reference temperature, so let's say, for example, I told you at 20 degrees, it's a nichrome wire. And then you just go to the first page and then find, okay, what is resistivity for nichrome wire at 20 degrees? And then part B would be, okay, so now the temperature increases to like 100 degrees. What's the new resistivity? So now use that. And then what's the new resistance? So now plug it into here. And then what's the new current density? What's the new current, et cetera, et cetera, et cetera. Okay. So, yeah, so it's basically you'll have two kind of separate parts for that kind of stuff, but. Okay.
So the resistivity and the rho and the coefficient of thermal resistivity are two values that we are.
Correct, so those would both be on the front page. Yes, yeah, so I'd have to tell you what alpha is, I'd have to tell you what rho is, I'd have to tell you those things. At least rho at whatever the initial temperature happens to be. Okay? So those are two long problems. The third long problem then is, let's see, I remember what I did. So if I had to guess, and I was a betting man, which I'm not, but that's fine. So it would either have to do with something like this. Capacitors in parallel in series with the definition of capacitance, as well as energy stored, and possibly dielectrics too, just for funsies. With this, that would probably be what I would guess for long problem number one. Now, if it wasn't that, then my second guess would be step two. My second guess then would be the same kind of idea, but with resistors instead. That would be my guess. Yeah. But we go back to here, because I specifically wrote this thing down. Which one do you think it's going to be? Capacitors, great. So the first part would be, here's an electric field between some two capacitors. Use that to then derive the capacitance. So do an integral. Find the capacitance. When you have that capacitance, then I'm going to put that thing into a circuit and then make you find all kinds of other stuff. Like what's the equivalent capacitance, what's the equivalent charge, what's the charge on each one of the capacitors, what's the potential across each one of the capacitors. And for funsies, let's go ahead and put a dielectric in there too, so that's going to change everything and then have fun then. That's what we go. Okay? Long problem number two. What about the short ones? So short ones are going to be things like, nothing really there. So one short one is basically just kind of playing with ideas of resistance and resistivity and things like this. So basically this would be then a short one. So, calculation, short answer one. Another one would be, probably because I didn't mention too much of it, but probably things with the batteries. So this would also be possibly a short answer one. And then if I didn't ask you things about parallel and series or resistors, then I would actually bet that would then be a short answer one as well. So I would bet that this would also be a short answer. So if I ask you parallel and series for capacitors, then I'm going to show up to somewhere with parallel and series for resistors at some point as well. Now that brings us then finally to RC. RC won't be part of the actual exam itself, but it will show up on the extra credit. So that means this would be something to do with extra credit. Okay. Now this exam is a lot easier, as I'm sure some of you have already noticed. A lot of this stuff is just kind of blind manipulation of equations. You don't have to understand everything as much. So it's a lot more just kind of plug and chug and find this algebra as opposed to really in-depth heavy kind of thing. So this exam is typically a nice one to make up a whole bunch of functions. So the average on this one usually goes up nicely. Okay, any other questions? No, where's okay? This one's usually pretty easy, so it's a nice place to kind of make up some points for. So let's start talking about some group assignments then. So this is the first of two Kirchhoff loop rules that I have So this one says that we have this circuit below where R1 is equal to 100 ohms, and then R2, R3, and R4 are some multiple of that. So R2 is 200 ohms, then R3 is 300 ohms, and then R4 is 150 ohms. And then the batteries in this case are E1 is 15 volts, and then E2 is equal to 10 volts. And I'm just going to ask you one simple question: what's the currents through each one of these resistors? Now, if I did something like this on the exam and I asked you what was the current through each one of these individual resistors, just because there are 4 resistors doesn't mean there's 4 currents. Some of them will have the same currents because they're connected in series. So in this case, which ones actually have the same currents? 1 and 2, right? 1 and 2 are connected along the same leg, which means they have to have exactly the same amount of current going through them because they're in series. This one here is a junction which goes to this junction, so this guy has its own current, and I have a junction going from here to here, which means he has his own current, so I have 3 total currents. So just because I say what's the current for each individual resistor doesn't mean each individual resistor has a different current from another resistor. Which means I have seen way too many times in the past that if I ask something like this, what will happen is somebody will say, here's a resistor, here's the battery, here's the resistor, and then they'll say, okay, current I1 is going through here, and then current I2 is going through here. Too many times I've seen this. No, they are in series with each other, so they have to be the same currents. So just because I'm asking you what's the current through each resistor doesn't mean each one has to have a different resistor. Now, if I also give you something that looks like this, what you can do is you can actually redraw this diagram to make it look more like something we've seen before. And to do that, basically what I'm going to do is just pull this guy down over here to move this junction here, and then move this one so this junction is in line with him. Which means if I wanted to make it seem a little easier, what I could always do is I could always redraw this. This way. These are exactly the same circles. So this was R1, E1, R2, R3, R4, E2. These 2 things are the same. So you're allowed to move things around as long as you don't spoil the overall geometry. So what do I mean by that? What I mean is you couldn't move this leg over to here because that's now completely changing the circuit. You can make small movements because we don't care about the length of the wires, because the wires, as far as we're concerned, have no resistance in them. So it doesn't matter if I lengthen them or shorten them. It doesn't change the overall resistance of the circuit, which means it doesn't change the currents. So I'm allowed to move things around minimally as long as I'm not, again, shifting things majorly to move this guy to the other side, because that would be completely changing the geometry of the circuit. Okay. So good, so that's it. So that's all this one is saying is here. Again, I know the right resistances. I could redraw this guy and then find the 3 different currents. Basically what this is asking, and then again, I know this is in series with this one, which means these 2 have to have the same currents. So just whatever current I find through, we call that I1, then each one of these just has, again, the same currents. So that's it. So that's that one. And then the second one, here's problem 2. Same kind of thing. So again, here I have these resistances. So these have really small resistors, but I have a 1 ohm resistor anywhere it's an R1, which means I have 1 ohm, 1 ohm, 1 ohm, and 1 ohm. And then a 2 ohm resistor at R2, which is only this guy. Here I have 3 batteries though. So this battery is 2, this one is 4, this one is also 4. And in this case, we want to know what are the currents, both magnitude and direction, meaning what are the directions of all the currents. For example, is this one going this way, this one going this way, and this one going this way? Well, of course they can't, because then I don't abide by the junction rule, which means that one of these currents has to be going in the opposite direction. So I want to know what direction are they moving, and what are their magnitudes, and then finally I want to know what is the potential difference between the 2 junctions. That's all I want to know. Now, when you talk about the potential junctions or potential difference between 2 junctions, the point is that, again, because I have a junction, that means anything along this branch here has the same potential as anything along this branch here, which has the same potential along anything along the branch here. Because they're parallel, they have to have the same potential. So if I want to know the potential difference between these 2 points, I can either use this leg, or this leg, or this leg, because they all have exactly the same amount of potential. Doesn't matter which one I choose. The rule of thumb that I like to use is which one has the least amount of current. What's the simplest? In this case, the simplest is right here. I have 2 elements. I get a potential gain here. I have a potential gain or drop depending on the direction in which the current is going. I only have 2 electrical objects. That's it. This one I have 3. This one I also have 3. So it's just easier to calculate it through the middle because I just have less things to calculate. But again, I can use any one that I want to. So if in the Kirchhoff rule problem that happens on Monday, I ask you what's the potential difference between 2 points, again, you can choose any one of the 3 legs because they all have to have the same potential because they're all in series with each other, or sorry, all in parallel with each other. It doesn't matter which one you actually choose. So in this case, you say I start here, I go up, potential increase, the potential decrease or increase depending on the direction in which the current is going, and I get to there. So my change in potential is simply the summation of those 2 things. Right? Great. So that's it. So I'll put up the first one again, so you can work on that, or you can ask me questions on any of the other ones, or work on those. Completely up to you what you want to do. You get basically 9 minutes to do anything that you want. Take a nap, comb your hair, brush your teeth if you got to this morning. Water. Okay.
The first one is E1 at 10 volts or 15 volts.
E1 is the first one that shows up, which is 15. So this is telling you in order. So it's E1 and E2.
Okay.
Yeah. What's up?
I don't have to, we don't have to redraw it, we can just put a junction there, just draw it, like.
Yeah, you just do all the usual things. Yeah.
Like, draw it like that, and then you can draw it like that,
Yeah.
and then you can draw it like the whole thing like that.
Yeah. Yeah.
And that makes sense because I don't know if people do two different currents, because there's not a junction between all one.
Yeah. Again, I think just people say, okay, I'm asking specifically what's current to each of the different resistors.
When you're doing the currents between R1 and R2, R2.
What do you mean?
Like, so like the current.
Well, R3 would be included if you're doing the loop. And in that case, yes, because I have to go through a closed loop.
Yeah.
So for example, if I use this loop, then my closed loop is, so yes, it would have to. And then for the second loop, if I did this, then it would also be included in the second. Yeah. So as long as I'm doing 2 closed loops. But if I do 1 closed loop, let's say this one, and then the outside perimeter one, then the outside perimeter would not involve R2.
Okay. Just any two like.
Any 2 closed loops, yeah. What's up, Paige?
Question, so when you rewrote that, you
Yep.
did R2s.
Yep.
R4 up top there. Parallel to each other. When you use the R-
Well, no, because if I put R3 down there, I'm moving it now to this level. Right, so what happens is R3 is between 2 junctions. It's not in series with R4. So if I look at this, right, I have a junction here, which means current go through in this direction, and then stop here. And then because of this junction, some of them is going to go in this direction, some is going to go in this direction. So if I put R3 over here, I've completely changed the geometry. So now I have gone from something which was in parallel to now something which is. So I just have to divide by where we
the biggest thing is, and I don't think that.
Well, that is what we would be talking about. So this would just be that. So for example, this would be the resistivity at 20 degrees. So for example, I was given a nice girl. So this one is going to be a jumper, and this is gonna be the number at that date. So it's just saying that I'm evaluating this at that. So it's not just
Yeah.
Yeah, exactly.
It's like.
Oh.
Glass.
No, in this case, it's, yeah, resistivity. So this is the thing that. So now that what happens is, as I'm running current or wire, the wire heats up. So as the wire heats up, that changes the resistivity, which there. So that's all I think. So let's say, you know, if I leave the wire hooked up for a while, this is gonna increase.
I know, we-
So now I'm just asking, okay, so now if it's already something to freeze, so the new resistivity. Right, the output is just what I'm saying. So, and then output's just gonna depend on that. So hopefully today,
Yeah.
as I'm talking to my wife, she's not feeling that great, so she's actually going to the doctor that. So it shouldn't be a problem, so we should be able to meet around like 5-ish, but, I'll talk to her, and then when I talk to her, I'll send you an email, and then we'll just have, you know.
I have more questions.
So it's good.
I was, because I changed my technique, and now I have a Spanish physics book, and I'm trying to understand the concepts. So
Okay.
I can know what you're talking about.
That would definitely help.
So yeah, now I have to just probably 20
Yeah,
minutes.
So now I'm gonna do problems. Yeah. Okay, sounds good. And like I said, this exam is kind of a good one because it doesn't involve as much conceptual understanding as the previous one. So this was one, yeah, where you can catch up with some points and get some good points out of it.
Yeah, I hope so. Okay, I'll try to, I don't know if you have some more examples, so you can solve it, so you can explain.
I'm sure I can come up with things.
Okay,
Okay.
I'll just, yeah, give you heads up for.
Yeah. Yeah, like I said, I should be able to email you around like 3 o'clock. Okay.
Thank you.
So really, this would just be 911 equals 0. Well,
Well, remember, it has to be a whole closed loop.
oh,
So,
yeah, just be from,
right, so it just can't be from here to here because that's only, that's part of the loop.
okay,
So in this case, I would have to say, you would look at this loop here. So in this case, if I say this curve goes in this direction. Right? So in this case, I would have.
yeah, because there's nothing on both sides, yeah.
That's it. So I'd have a minus I1R2 plus E minus I1R1. And then let's say the curve goes through here in this direction. So then I would get a minus I3R3. If I go through this loop, then I would get a plus, minus, and then minus.
Or this,
Or that's correct.
yeah,
Yes.
but that's just a lot.
So either one is fine, but yeah, but just going from here to here is only one leg. It's not a total closed loop.
All right.
So the change of potential equal to 0 is only true for an entire closed loop.
For some reason, I feel like